Hello everyone, welcome to our new video. Now in this video we will continue with continuous distributions and start with some examples from the normal distribution, which is one of the most commonly used distributions in statistics. So regarding the normal distribution, we have a few very useful functions in R, and here is the list of these four different functions. The syntax is again consistent with other distributions. You have these initials D, P, Q, and R that represents the density, the probability, quantile, and the random. For the random number generators, we can use these different alternative functions. So, for example, if we want to let's say evaluate a standard normal density function, we can input the mean 0 and standard deviation equals to 1. But if it is not standard normal, then you can change and input other values for the d-norm function. So here in this example, I am setting up a grid for my x-axis to evaluate my density function at multiple values. So you can run this line, and this code creates a sequence of numbers starting from -4 all the way to +4, and I set the length as 50. So we have a grid, an x-axis grid, which contains these equally spaced 50 x values. So once we create this, in the next step, I calculate and evaluate my normal density function at these points, and that also gives us another 50 values for the normal density function, and we can create a plot using these numbers. So the plot will look like this one, and you can increase this range of values. You can make it from -5 to +5, for example, or you can have more observations on the x-axis by increasing this length. Okay. And if you want to change the mean and standard deviation, you can, as we said, replace these with the values that you want. And then you can evaluate another normal density function with the given mean and standard deviation. If you are trying to calculate a specific probability, such as the probability x is less than 1, where this x is normally distributed with mean 1 and standard deviation 2, for example, then you can use the p-norm function and input the specific value you want this cumulative distribution to be evaluated, and this is equal to 1 for this example, and this will give you the desired result. And if you want to change, for example, since this was the center of the distribution, probability that x is less than 1, that's 1/2. Suppose we want to evaluate probability x is less than 2, then you can change this again depending on whatever is the mean and standard deviation for your random variable. You can update these and evaluate at the threshold given here. And we will get this 0.69. By the way, also we can standardize our random variable. We can standardize and replace it with z. So we need to update, in that case, our threshold value. So we need to subtract the mean and then divide by the standard deviation if you want to work with the standard normal random variable. But otherwise, if you want to directly get this result, you don't need to standardize, and you can just input the right values and evaluate the cumulative distribution function. And what about if you want to calculate the probability that x is in an interval from 1 to 2? Then this is same as probability x less than 2 minus probability x less than 1. And this is given by the difference of these two values. Again, with the appropriate mean and standard deviation for your x. And you can evaluate that, you get the result. If we are trying to create a plot of normal density function for a specific normal random variable, let's say with mu equals minus 3.5, sigma equals to 0.5, then I'm going to generate a sequence of numbers in my domain accordingly. For example, if the mean is around minus 3.5, I can start this from minus 5, or I can start from minus 5.5. You can adjust this as you wish. And then you evaluate your x values that are created. We have created 300 of them. We input into our density function, again with the appropriate mu and sigma that we desire. So you can evaluate this. And finally, once you get your y values, x values are ready, y values are calculated, then we can input x and y values and specify some additional options like the type of the line, the title, x and y labels, etc. These are some optional arguments for your plot, and that will create a new normal density plot for you. And you can also add additional lines to display, for example, the 1 standard deviation away from the mean. You can subtract the 1 sigma, and you can add 1 sigma to your mean, and you can create these vertical lines. So this one is adding vertical lines around 1 sigma of the mean. And you can just update your plot. So let me just run it again. So we will see these additional lines. We can put some legend here with the appropriate line type numbers. Mean minus sigma is here. Mean plus sigma corresponds to here. Quantiles can also be easily calculated using the Q-norm functions in R. If you are working with a standard normal, you don't need to input the mean and sigma. It's 0 and 1 by default. So you can simply input the probability, 0.15. So this means minus 1.03. So in other words, the probability that z less than this value equals to 15% probability. So as you see, in a quantile operation, we input the probability and obtain the value from the x-axis. So this is an inversion operation. And you can update this with other values of mu and sigma easily. You can generate random numbers from the normal distribution. You need to input how many random numbers you want and input what's the mean and standard deviation for your normal random variable. Again, the defaults are 0 and 1 anyway. I don't need to input these actually, but just for completeness, you can change these and generate another normal random variable. So for example, we can generate this. And then once we generate the normal random variables, we can check the histogram and verify whether the distribution looks like a normal distribution. So we can run it and see the histogram. This is the histogram that is coming from the z values that we generated. Additionally, we can actually use a so-called QQ plot, which is a quantile to quantile type of plot, and that is useful to verify whether your data set follows the QQ line. Basically, that displays the theoretical normal quantile to quantiles, And here, if we see that our points follow this line closely, roughly speaking, we can conclude that our values, our sample is coming from a normal distribution. Okay, but if we see too many deviations away from the line, then this will be an indication that our sample is not coming from the normal distribution. But this is just a visual inspection. Of course, there are some statistical goodness of fit tests we can conduct to verify more rigorously whether a sample is coming from a normal distribution or not. But usually, a visual inspection is your first step before you do the more comprehensive statistical testing. And in the remaining examples, I show a few things about the student t-distribution and exponential distribution, and we will conclude this video shortly. There is also a few useful t-distribution, let's say, functions that are available in R. Similarly, the initials are the same, d, p, q, and r, and then basically you just have t. These are the relevant functions for the student t-distribution. There are a few examples here. For example, if I want the quantile, 95% quantile for a t-distribution with 2 degrees of freedom. Remember, the t-distribution have this additional parameter that's about the degrees of freedom. So you can input this and use the, again, the probability that you want to get this x value from the t-distribution. And if we evaluate this, we will see 2.91 that corresponds to our x domain. That gives us the probability that our t-random variable less than this number equals to 0.95. So equivalently, we can write this as, let's say we have a random variable less than 2.9199. So this is equal to 0.95. That's the meaning of quantile operation. And you can also calculate the similar value from a normal distribution, and if you run it, you will see 1.64 is the corresponding value for a normal random variable. You can play with these degrees of freedoms. You can change and evaluate different numbers. As you see, if we increase the degrees of freedom, our value is getting smaller. Our basically value from the domain of the t-distribution, that's getting smaller. Finally, we have a few examples for the exponential density, which is another continuous distribution. And for this one, you will use the d-exp, and that is the density function for the exponential random variable. As you see, in the exponential random variable, we just have a single parameter that's called as the rate. This is basically the average expected waiting time. You can use the exponential density, especially when you want to model the waiting time. It might be, for example, the waiting time of a customer in a restaurant. And if you collect this kind of sample, you might try to use the exponential distribution to model the waiting time of customers. And the average rate is given as 1 as default value, but of course you can change this to any number that is relevant for your problem. So here we see that the domain of the exponential is positive. It must be on the positive real line. So we can set this as 0 to 10, and we have 200 values in this domain. So we are setting up the grid for our x values. So once we set up the grid here, then we will evaluate the density function of the exponential. Let's say our rate parameter equals to 1.7. Again, this is an hypothetical example, and you can plot your x and y values once these are calculated. you can define your x limit, y limit, and also include some labels for your x and y axis. So if we plot this, you see this is the exponential density function. You don't need to go beyond very large values on the x-axis because this decays very quickly to 0. So the probability for very large x values is essentially it is 0. So it already becomes extremely small. And here we can also use the cumulative distribution function for exponential random variables. For example, we can calculate the probability that an exponential random variable x is greater than 2.5. This is equivalent to 1 minus the probability x is less than 2.5. And here, suppose the arrival rate is 1.5, so we use this parameter appropriately, and then take this difference. So our probability here is about 2.3%. And if you want to use the quantile function, just like similar to the other distributions, just follow the same idea, and this time the parameter for your exponential is given here as 1.5, and then you will input the probability and you will get a value from the x domain. So for example, we get 3.07 for our quantile number. And random numbers, of course, random numbers with REXP function will give you the random numbers from the exponential distribution. As we have done for the normal distribution, we use the R norm and input the mean and standard deviation here to sample random numbers from normal distribution, as you see. Again, once you generate or simulate this data set, you can do all sorts of statistics operations like calculate the mean, standard deviation, median. So these are again all the same as we did in the previous videos. If you want to standardize a random variable, which is often useful, especially when you work with a input data set, you want to standardize your variables so that different variables are more comparable with each other. And you will subtract the mean and divide by the standard deviation of your sample to standardize a random variable. So once we standardized our random variables, the next thing for our later on videos, we will be talking about hypothesis testing. So if you want to create a confidence interval, you can actually calculate first, first we are actually generating a data set here. So after we have the data sample, then we are calculating our sample mean and sample standard deviation in this example. And then we divide our standard deviation with the square root of the sample size. So here my sample contains 100 observations, and I calculate my standard error here by dividing the standard deviation with the square root of n. And standard error for this sample average estimator is given as 0.19. So if you need to get the critical values from a normal or from a t-distribution, you are going to use the quantile values, because quantiles give us the value from the x domain for a specific probability. So we will be talking about these more when we discuss the hypothesis testing. So we can easily calculate these critical values from the t-distribution, or we can replace this with Q norm to calculate a critical value from a normal distribution. So these will be useful when we do the hypothesis testing. So Thank you for watching, and we will continue in the next video.